Okay, I'm going to talk about the core inputs sheet now for RTran. I'll just make it a bit bigger so we can see, and I'll go from top to bottom. So this is the sheet called core inputs that RTran expects to read. Always in this sheet, the second column is the name of the parameter, the third column is the value of the parameter, and the fourth column is notes about the parameter. RTran only reads the second and third columns, so the name and the value. So the first parameter is a parameter called grid square edge kilometers, and in this example it has a value of 1.5. So this is just saying that the edge of each grid cell is 1.5 kilometers. So if I just skip to the trips sheet, and I'll just make it bigger again. So you'll recall that always in RTran, each of our traffic zones is a square, like a grid cell. All we're saying is that the sides of each of these is considered to be square. It looks rectangular here, but in actual physical space, it's 1.5 kilometers along each side. So you can change that by varying this parameter here to make those grid cells as big and small as you like. The next parameter is called captive travel share. In this example it's 0.2. RTran doesn't have a separate car ownership model as you would find in the usual full commercial transport modelling software. In RTran at the moment anyway, all you can do is specify this parameter which says what proportion of the population does not own a car. So 0.2 is saying that 20% of all trips are made without the option of a car. That is, so they have to go by walk, bike or public transport. Car's not an option for this proportion of trips. And that's actually assumed to be the same across all grid cells, so that 20% of trips from each cell can't be made by car, have to be made by public transport or walking or cycling. Okay, the next lot of parameters underneath the heading generalized cost parameters. The first one's walk bonus and the next one's bike bonus. I'll talk about them both together. So walking and cycling are treated quite simply in RTran. The generalized cost of walking is this walk bonus plus the per kilometer walk cost, and that's specified in a sheet that I've talked about before. So this walk bonus is just an adjustment to the generalized cost. So you may recall previously there's a walking cost per kilometer. Let's say that's $5 a kilometer for argument's sake. So this walk bonus just adjusts the generalized cost. So here it's 1, which means that a trip of 1 kilometer would actually be $4. It would have a generalized cost of $4. That's $5 per kilometer, but we subtract this walk bonus. It's just an adjustment. Bike bonus here is actually negative, so let's say the bike cost per kilometer is $4 per kilometer is the perceived cost of going by bike. When we calculate the generalized cost, a 1 kilometer trip will actually seem to have a cost of $11. So it's this 7 plus the 4 for a kilometer, so it's $11 generalized cost for a 1 kilometer trip by bike. Next 5 parameters are all to do with cars. The first one says what's the cost per kilometer of driving. So you might like to think of this as petrol costs, but it can include wear and tear, whatever you like. It's just the per kilometer cost of driving. The next one is car revenue. So this is to allow government taxation or say fuel excise or something like that. And it allows you to impose a per kilometer levy or tax on cars. So this will increase the cost of driving, and so that will feed into people's decisions about whether or not to drive, but it will also RTran will also keep track of how much revenue you get. So when people do drive, they're charged this cost per kilometre, and that goes to government revenue, and that'll be calculated when RTran spits out the answers. The next parameter is a really important value of time. So in this one it's $15 an hour. So that's used to translate all times into generalized costs, to convert between basically time and money. Time is valued at $15 an hour in this modelling. You can change it to whatever you like. Next one's car costs per trip. So this doesn't have to be a monetary cost. This is, again, a generalized cost. And here it's 75 cents. So there's a 75-cent sort of just a bit of time finding your keys, getting into your car, doing, I don't know, taking it out of the garage. So there's a bit of time or effort or inconvenience in getting the car out. Last one's car revenue per trip. So this is like the car revenue per kilometre, but it's just a once-off per trip. So let's say, for argument's sake, this is a silly example, but it's the easiest one to make the point. If every time you turned your key in the engine of your car and the government charged you $1, let's say, you'd make this one $1. So that's saying there's a $1 revenue to the government each trip you make. Okay, next set of parameters is the generalized cost parameters for public transport. The first two are the average distance that you will walk to a bus stop. In this case it's 0.51 kilometers, and the average distance you'll walk to a rail stop is 0.75 kilometers, or 750 meters. So these will of course need to vary depending on how large your grid cells are. These are the distances that you'll walk within a cell. So if there's a bus stop within the cell, that's how far you will walk on average to get to a bus stop or a rail stop. The next one's the wait for in-vehicle time on a train. So if you spend 10 minutes on a train, a wait of 1 says that train time is valued the same way that car time is valued. So 1 hour in a car, if we just go back to the value of time, $15. Time is valued at $15 an hour. You see we specified here. So 1 hour in a car is the equivalent of $15 perceived cost. 1 hour in a train, specified here, is also $15 perceived cost. Whereas we see the bus is 1.1, it's weighted slightly higher. So 1 hour spent in a bus is actually $16.50 perceived cost in this model. The next one is any additional trip penalty you want to include for catching public transport. So for whatever reason, people may not like catching public transport, and so you can add effectively a perceived cost here. And in this model I have a perceived cost of $1 for catching public transport. Next one's a transfer penalty of, in this case, $1. So that's not a monetary cost, that's just if people have to transfer from one bus service to another, people don't like doing that, and this parameter specifies they perceive that as equivalent to a monetary cost of $1 when they have to transfer. That's besides the other costs, of course. So when you do a transfer, you need to get off one bus and wait for the second bus, let's say, if you're transferring to a bus. And so that waiting time would be taken into account and as part of the generalized cost. This transfer penalty is in addition to any other costs that are incurred that relate to the transfer. Next one is the actual bus fare. So here it's $1.60 for getting on the bus, and next parameter, train fare, is the same. Just to hop on a bus or a train in this model costs $1.60, and then 10 cents per kilometre for both bus and train, specified in the next two parameters. So you're limited to your fare structure for public transport in RTran. It has to be a one-off boarding fee and then a per kilometre cost. The next parameter is integrated PT fares, so integrated public transport fares. It's set to false here. You can set it to true instead. And this basically governs how people are charged fares. So if you have integrated fares, so if you set this parameter to true, people are not charged when they transfer. So they're not charged the boarding fee when they transfer. So if you catch one bus and you hop off and you catch the second bus, you're not charged that $1.60 boarding fare for the second bus. You're still charged 10 cents per kilometre, but you're not charged the extra boarding fare if you transfer to a bus or a train. So no matter what the transfer is, you're not charged beyond the first boarding, if this parameter is true. If it's false, you pay separately for every boarding. Next two parameters are the stopping time per second. So obviously buses and trains need to stop at bus stops and train stops, and that slows them down. They need to stop, pick up passengers, and then speed up again. And these two parameters say how many seconds in each grid cell are lost to stopping. So of course that will depend on how big your grid cells are. So if you have really large 10-kilometre grid cells, there's probably going to be a lot of bus stops and train stops by your trains, and so you're going to need to adjust these to take account for the fact that you'll have more bus stops within each grid cell. The next two are bus and train operating costs. So here I've specified bus operating costs are $1,200 and train operating costs are $16,000. Now these are specific to the period that you're modelling. So in RTran you could be modelling just the peak period, or you could be modelling all day, and of course that will then feed through to which costs you want to put in here, what numbers make sense. So these bus and train operating costs feed into the financials at the end. So when you specify your bus and train routes, RTran will calculate how much it costs you to operate those bus and train routes at the frequencies you've specified. If you specified that there's 6 trains an hour or 6 buses an hour, RTran will work out, okay, how many buses do you need to serve that route at 6 buses an hour, and how much does that cost you if it's $1,200 a bus. And then it'll balance that up against the fares that you receive on that bus route or train route. So you'll see each route, whether each route makes a profit or a deficit. The last 5 parameters I'm not going to talk about in great detail, or some of them I won't talk about at all. The first one, the OD match iterations, I won't talk about, I'll skip for now. Okay, I'm not going to talk about the $/utility conversion denominator. That's just to do with the generalized cost modeling, converting between dollars to utility in the utility maximization models, the random utility models. Model congestion, this is actually quite a big one. So if you set it to false, then RTran won't bother modeling congestion. So effectively it assumes that the capacity on the road network is infinite. There's no slowdown due to congestion. If you set model congestion to true, then RTran will take into account the numbers you've specified in the road capacity sheet. So I'll just flick over to the road capacity sheet, and you'll see it, I've put some numbers in here. Every grid cell can accommodate 68,571 cars in the model period. So there's a free flow speed or an uncongested speed of 40 kilometers an hour. That's specified in the car speeds sheet. But as the volume of traffic approaches the capacity, then that speed will actually slow down. So if you model congestion, RTran will take account of those road capacities, and this will actually cause RTran to run a lot slower if you do set this to true, and that's because RTran needs to go through more iterations when it runs just to make sure that there's equilibrium on the road network. At this point, hopefully you should be able to look at an existing user input spreadsheet like the one that comes with RTran and understand basically what's going on and what the simulation is.